Hi, my name is Pedro Lopes, and today we have 5 new Chi papers from the Human-Computer Integration Lab for you. This is Myoaction. This is the first paper led by Yudai Tanaka. He's going to speed up my reaction time. But first, to show you how hard this pen falling task is, let me do it with my uninstrumented hand. Give me a second. Okay, it's very, very hard. Now, I'm wearing Myoaction. Using electromyography is going to speed up my reaction time because the moment he detects my intention to move with the muscle signal of my own muscle, he stimulates my muscle. And that's going to generate a faster reaction time and hopefully catch the falling pen. All right, I got it. I felt the muscle stimulation impulse just in time as I was thinking about moving. The reason why this works is because muscle stimulation movements are actually faster and they rise faster in speed than voluntary movements. That's how Myoaction can do this. Now, Myoaction can do another cool thing, which is the following. Preserves my intention. If I don't want to move, there's no intention to move, there's no muscle signal, there's no muscle stimulation. No other muscle stimulation system was doing that before because they were all pre-programmed to speed up users' action. Thanks, Yudai. All right, the next paper is one that takes muscle stimulation to more complex territories. Not only like simple tasks like this one, but really complex instructions like cooking and spray cans and painting things and so forth. This is a system called Generative Electrical Muscle Stimulation, in which we actually use an AI system to generate the instructions in real time. So it turns out I had another hand with muscle stimulation, but I promise it was not connected because I'm going to connect it right now. To make this more complex, Yun is also going to attach one more electrode to me that can control my index finger. And now I can ask the system for help in much more complex tasks than just like help me catch a falling pen. In fact, it can even see what I'm seeing. It can see the Yudai and Mithyl behind the camera, but it all can see the things that I have here. So for example, here I have 2 bottles, and I'm going to ask the system to help me with this bottle. So EMS, help me. Okay, so let's see what happened. It generated a bunch of instructions here, textual instructions. Object being used, spray can, likely to spray. This is a lot of text, classic LLM usage. Now we're going to convert this into things that are really about movements. And we keep refining and refining and refining these things until we're able to create muscle stimulation commands that are biomechanically compatible with my own pose. At the very end, we have muscle stimulation commands. Let's see what happens when Yun, can you, give me a second. Can you play out the commands on my hands? Wait a second. Ah! Do it again. Goes down, goes up. Nice. So what it's trying to say is don't forget to shake the spray can before you shake it. Now, if this is truly generative, you should find out another context. Even if we make it super hard and we put another spray can in white, not revealing that it's actually cooking oil. So let me try this again. EMS, help me. Play it. Okay, I sprayed the croissants, but I also sprayed the USB cable. So as you can see, this time, the instructions here don't have any shaking movements because we're talking about croissants, and the system, using the vision language model, quickly understands that this is likely a cooking oil spray can. And it really is. Canola oil. All right, thanks, Yun. This paper by Yun and Romain Nith has received the Best Paper Award at this Chi. Now, we're going to try to keep pushing EMS to its limits using a system that requires us to set up a few more things here. This is a paper by Lonnie Chien, who was a master's student in our lab and is now going to Cornell University to do his PhD. And this takes these devices to an extreme scenario. I'm going to remove these 2 electrodes because I won't need these ones. And we're going to start the demo. So what do we see here? We see that with my hand, I'm going to put my other hand down so it doesn't get confused. With my hand, I can control this slider right here. This is what Lonnie and I call an embodied device. I'm controlling the volume of my computer, the stocks that I'm buying, whatever variable I want, using my hand. But notice that I'm not looking at that slider. So how do I know where it is? And how do I know the possibilities that it affords? How do I know when it's at maximum range? How do I know when it's at bottom range? Well, we know this because our system is active and is using muscle stimulation right now. So if I push it down, I can't go lower than this. Look at my hand jittering. It's preventing me. I can feel, without having to look, what the limits are. The same on the top, and the same anytime I pass one of the stick marks. And more extreme, if I deactivate it, and now I started in the wrong location, it will automatically, there we go, move me up to the last point I used it. Muscle stimulation realigns the virtual interface state with my physical interface state. This is what we call embodied devices, which we explored in this paper. All right. The next system also uses muscle stimulation, but notice that we were catching pens, we were helping with cooking, we were controlling interfaces. Nothing was about forces. What happens if we try to teach someone a force with muscle stimulation? And that's what we're going to do here by trying to teach me how to take the perfect espresso shot. Mithil Guru authored this paper, and he's going to teach me this.
Hi, I'm Mithil, and today I'm going to teach Pedro how to tamp coffee grounds for a perfect cup of espresso.
Just a second, Mithil, because we're losing the electrodes. Go.
All right, get in starting position. And now it will show you how to do it.
All right, I felt a force that I should learn. Now I'm going to try to reproduce what I felt. Okay, I don't know what you guys are seeing here, but what we found in this paper is that people wildly overshoot. You're probably seeing that my reproduction of this force is so much stronger than the actual force. This is the first problem that Mithil found about teaching forces with muscle stimulation. But as good interface designers, we're asking, can we do better? So Mithil created a model that tries to compensate for this perceptual mismatch, my overshooting behavior. And will now, he's been trained on me already, showing me a different force so that I overshoot in a different way and I get the right profile. Let's try it.
Now it's showing again.
Okay. Can I go for it?
Yes.
All right, let's have a look. Okay, much better. So this is my new recalled force, what I felt this time, but because the model adjusted, I was able to not overshoot as much, and hopefully it gets almost as good as this espresso shot that I have right here. So this is the coffee grounds. So this is force EMS. If you need to use forces on your EMS system, muscle stimulation, please use force EMS. Finally, our last paper is a conceptual paper. What we're trying to give is a new challenge, a new direction for the field of haptic devices. Haptic devices right now, in the last decades, have been concentrated on the following approach. I put a haptic actuator, in this case a vibration motor, in the place where I need to feel the sensation. This is great if I'm touching a virtual object. Zzz, works perfectly. But what if I'm shaking hands with Yun? Now I have the haptic actuator and I can't feel the warmth of her hand. I can't feel this handshake. This is because we decided to optimize for the virtual side of haptics. In this paper, led by Shan-Yuan Teng, former PhD student in the lab, now a professor at National Taiwan University, we're arguing we can do different. We can optimize for the ability of a haptic device to still let me feel the real world. There's many strategies we can use. Here's one that we've published in the past, where the actuator allows you to feel through the device. So you can see there's some holes. So if I try to shake Yun's hands while wearing this, I can still feel some warmth and some texture. It's not perfect because this is kind of a compromise-based device. I can do other things such as this one. This one, completely free finger pad. But if I'm touching a virtual object, this device rotates and touches my finger pad. So this is like an on-demand actuator. Or a more extreme approach, put the haptic actuators in a location away from the important location, so finger pad free completely, but remotely trigger those sensations to land at the perfect location. This is here a paper by Yudai Tanaka, who's behind the camera. They use electrical stimulation to steer the sensation to the finger pad. And if I hold Yun's hand wearing this device, my finger palm, my finger palmar side, can feel all sensations despite the device being on the back side. These are different ways that we can move forward as a field by optimizing both real world haptics and virtual haptics. These are the papers that we presented at CHI 2026. You can check them on our lab page.